This is the Module 3 video on the conjugate addition of nucleophiles to electrophilic alkenes. I will begin by introducing the experimental details in a specific case, the preparation of succinonitrile. I will emphasize that I have no personal experience with this reaction, and in fact, I really wouldn't want to do it myself or have someone in my laboratory doing this. But it is useful to at least talk through what is happening here, and there are some mechanistic clues embedded in the experimental details. I'll add that we will use a 3-neck flask, which has a reflux condenser, an addition funnel, and a thermometer to monitor the internal temperature of the reaction mixture. For safety reasons, we'll set this up in a fume hood. I also recommend putting a water bath around the reaction flask to act as a heat sink. This will absorb heat from the reaction mixture, and you can heat or cool the water bath as needed. First, the experimentalists added a small amount of potassium cyanide. 60 micromoles corresponds to 1 mole percent of the anticipated amount of acrylonitrile and hydrogen cyanide reactants. Then, they slowly introduced acrylonitrile through the addition funnel. The experimentalists did not describe if there was any temperature change at this point. Presumably the temperature was close to room temperature. So they began adding liquid hydrogen cyanide through the addition funnel. They deliberately added only a portion of the total 6 millimoles that they planned to add. They warmed the water bath so that the reaction mixture temperature reached 30 degrees, and then the temperature kept increasing. And apparently at 30 degrees, or 300 Kelvin, there are now enough molecules with sufficient kinetic energy for this reaction. The reaction generates heat. As the temperature goes up, there are even more molecules that are over the energy barrier. This is why the water bath is used to keep the temperature under control, to avoid a runaway reaction. After they have the temperature under control, they add the remainder of the liquid hydrogen cyanide. And the reaction is complete after 2 hours, probably assessed by noting the disappearance of acrylonitrile and the appearance of a new product, which they purify by vacuum distillation to separate succinonitrile from the potassium cyanide catalyst. An isomer could have formed. 2-methyl-melanonitrile is a stable compound, but since they did not observe that, the maximum yield would have been 7%, and it probably was even much, much lower than that. With this information, I will now propose a mechanistic claim that begins with the Lumo of Acrylonitrile accepting electrons from a nucleophile. The nucleophile will be the reactant with the highest energy occupied molecular orbital. And so that is the potassium cyanide catalyst. I'll show a Spartan view of the Lumo of Acrylonitrile. This is the structure of acrylonitrile, double bond on the left, triple bond on the right. This is the HOMO with 2 pi bonds, one for the alkene and one of the nitrile pi bonds. And then to the LUMO, this has pi bond character in the center for the carbons connecting the alkene to the nitrile, as well as p atomic orbital character on the terminal carbon and the nitrogen. To show some other aspects of the structure, this is a HOMO again. Below that is another orbital, accounting for the second pi bond of the nitrile. And then at lower energy, there is an orbital which has considerable lone pair character on the nitrogen. Returning to the worksheet, we'll now begin by writing a mechanistic claim. The cyanide anion donates electrons to a carbon of the acrylonitrile LUMO. And the product of that step is a carbanion. But the carbanion is resonance delocalized with one of the adjacent pi bonds of the nitrile, so that the negative charge is shared between carbon and nitrogen. This anion has relatively high energy for its highest occupied molecular orbital, so it donates electrons to the LUMO of hydrogen cyanide to give succinonitrile and regenerates the potassium cyanide catalyst. Although this is the textbook mechanism, it's helpful to compare it with other possibilities that may be seemingly reasonable or connected with other things that you have learned. Turning to the next page of the worksheet, we can consider a mechanism in which the alkene is the HOMO and hydrogen cyanide is a Bronsted acid, similar to hydrogen bromide, as presented in Chapter 19. So the alkene donates a pair of electrons to hydrogen cyanide. This gives a secondary carbocation, and that may be resonance delocalized by the pi bond of the nitrile. But notice that neither resonance form of this cation has all atoms with octet fulfilled. We can explore the alternative in which protonation occurs to give a primary carbocation. And if cyanide anion adds to that cation, that matches the product, succinonitrile. In the class meeting, I'll ask you to present evidence that supports or disproves Claim A, as well as evidence that supports or disproves Claim B. And then we'll also discuss your reasoning in support or against each of these claims. Turning to the next page of the worksheet, in the class meeting, we'll transform the mechanism from the claim onto a reaction coordinate diagram. And we'll compare the reaction both with the potassium cyanide catalyst and the reaction without a catalyst, which we know from the experimental information no reaction occurs in the absence of potassium cyanide. Turning to the next page of the worksheet, this asks us to sketch the shapes of the HOMO and the LUMO for 3 alkenes, propene, methylvinyl ketone, and acrylonitrile. I've calculated the HOMO and LUMO energy values for each compound using Spartan. I will show videos created from Spartan that illustrate the shapes of the HOMO and LUMO orbitals of these three alkenes. This is the structure of propene. The HOMO has pi symmetry along with a small amount of carbon-hydrogen bond character. The LUMO has two p orbitals out of phase. Also, we see the carbon-hydrogen bond character. The p orbitals out of phase correspond to a pi star or pi antibonding molecular orbital. For the next compound on the list, this is the structure of methylvinyl ketone. The HOMO actually favors non-bonded electron character on the oxygen. The pi orbital is actually not the HOMO, but it is a level below. However, the LUMO has the character of pi between on the carbons between the alkene and ketone, as well as p character on the terminal carbon and the oxygen. Then we can revisit the molecular orbital depictions for the third compound, which is acrylonitrile, with the HOMO and the LUMO. Returning to the worksheet, I will now paste in the LUMO and HOMO orbitals for propene, methylvinyl ketone, and acrylonitrile. In the class meeting, we'll discuss how this information is relevant to the transformation of hydrogen cyanide reacting with acrylonitrile in the presence of potassium cyanide catalyst. This concludes the first video for Module 3B.